Welcome back to Math 135. This is Lesson 14 about graphing and applying quadratic equations. We've worked with solving quadratic equations and we've worked with some graphing in the past, and we're going to kind of run these together to get a stronger understanding of our quadratic equations. And I came up with a problem that I thought you might find a little bit amusing and somewhat instructive. We've got Monty Cobra catapulting plush toy cows off the top of a castle bulwark. That's a hard word to say. No animals are getting injured for this presentation. The stuffed animals flew according to this particular function, and I clarify for you that x is the horizontal distance away from the castle and y is the vertical height that these cows are going to achieve. Well, what I'd like to know is what's the maximum height that each of these cows attains, and how far away from the castle will the cows land when they hit ground. Now you get to watch one of these little cows go. Watch. Ah, there he goes. And you saw that in the pathway, because he was catapulted, he first went up, hit a high point, and then fell. Okay? So we're going to want to figure out exactly what's going on here. A quadratic equation graphs as a parabola, and you've already seen these parabolas in the past, and they might be opening downward or they might be opening upward. In both cases, we have this very important point called the vertex, and the vertex is going to be the very highest point or the very lowest point achieved within that particular curve. Okay? Now, to find that vertex, I'm going to give you a couple of options. But for this very first one, what we're going to do is actually complete the square. I went through that process on an earlier lesson, and it's going to be a similar process with a minor variation. So here's what I'm going to do. In order to find out this top point, okay? Hey, by the way, essentially, that cow started its flight right about here, partway up that parabola, and then went down through there. Okay? So, here's what I want to do. I'm going to factor this -1 out of the x squared and the 4x term. I'm going to leave the 12 hanging out there on the outside. Now I do the complete the square with this particular portion. And remember that because of the way a perfect square multiplies out, we have to take this and divide it by 2. Okay? Half of that to come down, and then you take 2 and square it to come up. Now you do have to be careful on this one. We've essentially made a change of a -4 in the equation at this point because everything inside of the parentheses gets multiplied by this -1. And it's sitting outside here. So I've actually made a -4 change. To balance that on the same side, I have to add 4. Because I don't want to touch this left-hand side. I want to leave the y by itself. So I have to balance on the very same side of the equation. And that would give me then a +16. So the given equation is identical to this equation. Okay, or it has the same solutions. It has the same pathway. Well, if you take a look at this, we've talked about transformations. And you might realize that this -1 is the a value that we've talked about in the past, and that a value flips it down. Okay. And so all we did was flip that down, and then this moves it right to, that's that C value, and this is the D value. We'd go up 16. So we would have actually this shape because he's opening downward, and we would go from the origin, we would go right to and up 16. So his pathway actually goes up through that point. Okay? Well, that means that I do know the maximum height my cow achieved. He achieved a height of 16 feet. Now he started, where did he start? Well, when he started, the x value was 0. So I can put that in very easily and find that he started at a y value of 12. So my little Cal started at 0, 12. Then he first shot upward, okay, until his momentum couldn't take him away from gravity anymore and it started to pull him down. And we end up at 216 at his maximum height. And then he's going to fall. Now, I'd like to know then, where did he actually land? Did he land at 4 meters, or whatever our units are, away from the castle? Well, what would this point be called as far as the graph is concerned? This point would be an x-intercept, right? Now, do you remember how we go about finding an x-intercept? Let's see. To find an x-intercept, you always put 0 in for y. Okay, so I'm going to go back to the original. 0 equals negative x squared plus 4x plus 12. Now I need to solve that quadratic equation. And I decide, you know, I like having a positive x squared better, so I'm going to multiply through by a negative 1. And I have 0 equals x squared minus 4x minus 12. And I say, oh, I like that. He factors really easily. X minus 6, x plus 2. So x is 6 or negative 2. Well, you know what's kind of interesting? You know, I said you kind of are starting partway up this curve. Of course, since it doesn't have an end, you had to start partway along the curve. But if it fell backwards, it would hit at negative 2. But going forward, well, my Cal didn't show quite as far as he should have gone, because he should have gone all the way over here to 6. So in fact, his pathway really would have been more like this if I'd gotten him animated just perfectly. And that actually is a nice curve for my Cal to have taken. And now we know how these other guys are going to go. And they're going to land 6 meters away from the bottom of the castle. Okay, well that was fun. So now we're going to just focus on doing some graphing of our parabolas. So here's the basic parabola, and I set him right at the origin because ordinarily for a basic parabola, just the basic y equals x squared, his vertex is sitting at the origin, and he goes through the points 1, negative 1, 1, and negative 1, 1, and has that nice upward curve. Now, because of this 3 and this 4, you know there are C and D in the equation, he would actually move 3 right and up 4. Yeah. So the vertex is sitting at 3, 4. And the equation of the line of symmetry, what? What about a line of symmetry? Well, it makes sense that there's this perfect line of symmetry that goes right up through the center of your parabola. It would be a mirror line where one side of that reflects over to become the other side. Well, that's going to be the vertical line that goes right through the origin, so it would be x equals 3. Now, to get my y-intercept, remember I have to put 0 in for x. Okay, well, let's get some space here and work. So if we put a 0 in for x, we have y is equal to 0 minus 3 squared plus 4. That's what, 9 plus 4, 13. So my y-intercept is at 13. And you know, that does kind of make sense with where this is sitting right now because I can see it's going to cross my y-axis up there a little ways. Okay. Now, it's a good idea to always write your intercepts as ordered pairs. Okay. X-intercepts. We know, take a good look at that graph. What do you think you have as x-intercepts? Probably none. Well, to get my x-intercepts, I'm supposed to put 0 in for y and solve and find out x. Well, with this particular arrangement, I would subtract that 4 over. Negative 4 is equal to x minus 3 squared. And then to remove this square, I need to square root both sides. And right there, I'd end up with the square root of negative 4. Now, there's nothing inherently wrong with that. I could find solutions. There are 2 solutions, but they don't happen to be real numbers. And remember, when Mr. Descartes set up this nice little graphing system, these are the real numbers. So, in fact, we never cross the x-axis. So, none. And then another question that you're often asked as far as your quadratics go, will that vertex be a maximum value or a minimum value? You know, in the case of the cow flying, that was going to be the maximum height he could possibly hit. In this case, that's the bottom. It's going to be a minimum. Okay? All right, let's try another one. In this particular one, we have f of x is equal to negative x squared plus 9. So I've already done the flip. What made this flip and open downward? Well, remember, that's when your a value is negative. If you've forgotten this, you might want to go back and look at those lessons about transformations. That's when we talked about how the numbers that are in that equation will affect the way the equation looks. So this negative 1 multiplied onto the x squared flipped him. And what's the plus 9 going to do? Well, it's going to move him up 9. So where is his vertex? Well, his vertex is going to be sitting at 0, 9. The equation for the line of symmetry, now the line of symmetry is always going to be that line that cuts right through that vertex and cuts your parabola into 2 halves that are mirror images of each other. And that will be x equals 0, because it has to go right through that vertex. Well, for y-intercept, I'm looking at it. Now, I know my y-axis kind of stopped, but that's okay. My y-intercept is 0, 9. Now, do you expect to have any x-intercepts this time? Yeah, I kind of expect 2. I expect to get 1 positive and 1 negative. Now, how do you get x-intercepts? Well, you put 0 in for y. So we would have 0 equals negative x squared plus 9. Add that over. X equals plus or minus 3. Well, my picture didn't come out perfectly there, but that's okay, because that picture, I'm not trying to use it to come up with any particular information, just to organize my thinking, and it works with my information. My x-intercepts are 3, 0 and negative 3, 0. And is this vertex going to be the highest the function hits or the lowest? Well, it will be a maximum value. Hey, by the way, while we're here talking about this particular point, sometimes you're asked for what is the maximum the function reaches. That would actually be asking you for the y-coordinate. You would want to give the y-coordinate. The x-coordinate is about the location horizontally as far as where it falls, but the highest it hits is going to be your y value. So if you are asked what's the actual maximum value the function hits or the minimum value it hits, you give the y-coordinate of that vertex. Okay? Now, actually, before I go on, what was really nice about these two particular equations that we worked with is the way the equation was written, okay? And so there are two ways you are most likely to see the equations of your parabola. One is what I call the vertex form. And when you see it sitting in that form, you really like it, because if you understand transformations, you know that A is affecting whether it's opening up or down, and it's affecting the vertical stretch or compression. That was back in that transformation lesson. The H and the K are your horizontal and your vertical translations. Now, since all of your parabolas are starting at 0, 0 for the vertex, assuming there's no transformation on it, then this will actually tell you where your vertex happens to be sitting. So whatever H happens to be, whatever K happens to be, I would move H and K, and there is my parabola after the transformation. So in this particular arrangement, you can pick out your vertex immediately as H comma K. Makes it a very quick and easy way to do graphing of your parabolas. Now, when they happen to be sitting in this arrangement, and this would be in a general or a standard form for a parabolic or a quadratic equation, and when you see that, it's not quite as friendly, okay, as far as just I'm automatically picking it out. But if we went through complete this square again, and I'm not going to do that because I did that for you in the previous lesson, or actually several lessons back. So what I'm going to do is let you know that when your parabola is in the form of ax squared plus bx plus c, the x-coordinate of your vertex will be sitting at negative b over 2a. Now, where have we seen that negative b over 2a in the past? We saw that in the quadratic formula. I told you at the time that you'd see that negative b over 2a again, and here's where it pops up. That will give you the x-coordinate. Now, by the way, if you want, go back and watch when I did that complete the square, and you'll see why my vertex has an x-coordinate of negative b over 2a. Well, with that information, this guy is actually easy to work with as well. Because here's my b value, here's my a value, so the x-coordinate of my vertex is at negative b divided by 2a, it will be at negative 3. So I'm actually happy with my parabolic equations given to me in either form. Of course, here I've got to work just a little bit. To get my y-coordinate, what would I need to do? Well, you could go and memorize, because you could get a formula for it, but it's kind of gaggy. No need to memorize that. Put your negative 3 in. Whatever your x-coordinate is, put it into the function. That's your quickest way to get that y-coordinate. So I would end up with 9 minus 18 minus 1. It's at negative 3, negative 10. Now, I don't have this guy set up that he's going to move for us. So I would just have to think, okay, 1, 2, 3, and I can't go quite down to negative 10, but I'm going to be way down here at negative 3, negative 10. Now, is he going to be opening upward or is he opening downward? Well, how do you tell? What's really nice is this A is the very same A that we see in our transformations. Since that is a positive 1, he's going to open upward. And he really does not have a stretch factor on there. Okay. Now, it's just kind of nice to have a rough idea of where he's sitting and where he's opening, how he's opening up. The equation of my line of symmetry is going to be x equals negative 3 my y-intercept, let's see here, to get my y-intercept, oh, I put 0 in for x, right? So I put 0 in for x, and I get -1. Well, yeah, he could come open that much, and especially if he was all the way down at -10. All right. X-intercepts. Do you expect any x-intercepts? Yeah, I expect 2. I expect 2 of them. And you see, that's a nice thing. You might look at my picture and say, man, her graph is just terrible. But that's okay. It's all I need. It's organizing my thought processes. So I say, okay, well, let's see here. 0 equals x squared plus 6x minus 1. That doesn't factor. Now, if he doesn't factor, I have 2 choices still to solve a quadratic equation. I can use complete the square, which I'd rather not do, or I can use quadratic formula. Yeah. So, -b over 2 times a. Hey, we did that just a few minutes ago, didn't we? And we got our -3. Yeah. Plus or minus the square root of b squared minus 4 times a times c, -4, all over 2 times a, 2. Well, that'll give me -3 plus or minus, this will be the square root of 40 over 2. And we've been doing some of this simplifying radicals, so I hope you're okay with me just saying that would be 2 square root of 10 over 2. You can do the dating game if you'd like on your own. Cancel those, and we get -3 plus or minus the square root of 10. And you know, I really kind of like that particular notation because we have a line of symmetry at -3, okay? And look at how cool this really is. From -3 to get to my x-intercepts, I add square root of 10, I subtract square root of 10. And you say, I can't deal with the square root of 10. Well, isn't that just a little bit more than 3? So you see, essentially, I go a little bit more than 3 to the right, a little bit more than 3 to the left, and that's where this guy, now remember, he's down there a little bit farther, but that's where he's going to cross the x-axis. They're definitely symmetrical with that line of symmetry, and it just comes together so nicely. So I have got 2 x-intercepts. They are -3 plus or minus the square root of 10, comma 0. And since I don't have a lot of space, I'll just write them together. Now, is this particular vertex a maximum or a minimum value? Well, that would be a minimum. And as it turns out, my absolute minimum value of the function, and you ought to jot this down just to make sure you have it, minimum value of the function is right here, -10. That's the lowest that function can ever have as an output. Oh, you know what? That's kind of talking about range, isn't it? It tells me, in fact, that my range is from -10 to infinity. Oh, isn't it nice when you can put everything together? Okay. Well, on this guy, I went ahead and put a stretch on it already. Now, it may not be as much stretch as it should have, but I've actually already put a little bit of a vertical stretch on it because I have an a value of +2. And even though this is sitting in the standard form rather than the vertex form, the a value is still the same in both arrangements. So where would my vertex be? Because this would be the graph of just y equals 2x squared. But because of these numbers, there's been a slide put on it. Well, in this direction, I do negative b over 2 times a. My x-coordinate is negative 3. Maybe I like negative 3s. Now, we have to put that negative 3 back into the function to get the y value. That's what this equation is all about, to generate outputs. So let's see here. If we're going to put in a negative 3, we'd have, what, 18 minus 36 plus 9, and I think that's a negative 9. I didn't mean for those to come out to be about the same spot, but they did. They're coming out to be real close in the same location. My line of symmetry would be x equals negative 3. My y-intercept, you know, it is kind of cool. In this particular arrangement of the equation, in a standard position, if you put a 0 in, it wipes those guys out really fast. And that c value is your y-intercept. So we're sitting at 0, 9. Wow, it's way up here. Look at what that does. But then again, this is kind of narrow, although it didn't really have a horizontal shift. What happened, or horizontal compression, what happened is the vertical stretch makes it appear to be horizontally compressed. I have no idea if I hit my intercepts where I was supposed to, but I'm very confident that I have 2 x-intercepts. So let's find those x-intercepts. And it's not obvious in any way as to where they're going to fall, so I have to work at it. Oh. Okay. 2x squared plus 12x plus 9 is equal to 0. Why do I have it equal to 0? To get an x-intercept, you let y be equal to 0. Okay. Now let's see here. I don't think this guy's going to factor. So we'll go to our quadratic formula. Negative b over 2 times a. That's my negative 3, right? Remember, the very first fraction in the quadratic formula will always give you that x-coordinate of your vertex. Okay. B squared minus 4 times a times c. Well, I think that's a 72. All over 2 times a. So we get x is negative 3 plus or minus the square root of 72 over 4. And I believe if you simplify that, you're going to get negative 3 plus or minus 6 square root of 2 over 4. And you could cancel the 6 and the 4. They're both outside of the radical. That would be legal. Negative 3 plus or minus 3 square root of 2 over 2. Okay. Well, I know that the negative 3 is great because that's my line of symmetry. And I need to go left and right from there. Now I'm going left and right, whatever this value is. Now I don't have a calculator in my back pocket, so I'm going to just make a wild estimate that this is about a 2.1, just kind of about a 2.1. So from here I go about 2.1 to the right, about 2.1 to the left. That's very, very acceptable, okay? So I have got 2 x-intercepts. They're not pretty, but that's okay. We're not here to judge. Negative 3 plus or minus 3 square root of 2 over 2, comma 0. And you know, in all honesty, it's not a bad idea in this case to come up with approximations. Okay? Grab that calculator and come up with it being about a negative 0.9 and about a negative 5.1, if I've estimated those well. And this vertex will again be a minimum value because he's on the very bottom. And it does mean my range is not all reals. My range is going to be from -9 up. Okay? Well, let's do some fun problems. It's always fun to do word problems, or at least I think so. We've got a farmer. Farmers always have to do algebra, you know. You've got 4,000 meters of fencing to enclose a rectangular lot, and it's along a river. Now, I came up with a picture of a river here, and it's not exactly straight. We're going to assume that that side is straight, and we have a nice rectangle. Okay, and we want to know what's the largest area that he can enclose. There's a couple of really important words in that. And I always suggest to students that when you're doing a word problem, the first time you read it through and you just kind of get a rough idea, this is something about a farmer in a field, okay? And then you go back and you start pulling out the important information, like I bet I'm going to need that 4,000 meters. It's important that it's a rectangle, and that I've kind of given. And the fact that I'm only going to use 3 sides, or I'm only going to have to fence 3 sides of that rectangular field. Now, right here is extremely important. We could get all kinds of areas out of this, you know, because you could take that 4,000 feet of fence and you could have 1 foot, and 3,998 feet, or meters, I'm sorry, meters. Or you could have something like, I don't know, 500 on each of these. Now that takes away, what, 1,000 of your meters? So that leaves 3,000 meters this way. Do these have the same area? No way. They're very different. And so interestingly, we can have the same perimeter but have very different areas. Okay. And we want to come up with whatever is the largest. Now, since we've been talking about quadratic equations, chances are we're going to get some kind of a quadratic equation out of this. And to get the largest, that sounds like a maximum value. The other very important key word here, and we have actually been talking about it, is area. The fact that I'm looking for maximum area, and you identify, that's what I'm looking for, maximum area. That means you will write an equation for area. You don't have to think this through. You're not left wandering out in the wilderness trying to find your way. You know what to do. You're going to write an equation for area. All right. So I need to get the area of my rectangle. Well, to get the area of a rectangle, you generally take length times width. Okay, I'm off and running. The only thing is, that's not what I'm going to use, L and W. So let's see here. You know, I was playing this game a few minutes ago about some possible numerical values, and sometimes that is extremely, extremely helpful. Because your common sense is generally much more comfortable with numbers than with letters. So play with a few more maybe. What if I put, let's say, 1,000 meters and 1,000 meters? Then how long is this side going to be? Isn't it 2,000? Now, by the way, how am I getting the 2,000? Do you know how I got the 3,998? The 3,000? Well, I got them because all combined, he's got 4,000 meters. And you know, these two have to be the same, right? So what if we had, I don't know, 50 and 50? That takes up 100 And so that would leave 3,900. Huh? Okay. Well, you know, since this can vary, it can vary, hence a variable would be a great idea. So how about if I call this guy x, and then this guy would also be x? And then what did I do every time to get this other dimension on my rectangle? I subtracted these two from 4,000. Okay, so 4,000 minus 2x. We're off and running because we needed to write an equation for area. To do that, we needed length and width, and now I have them in terms of a variable. Okay, let's write our equation now. Hey, don't forget this strategy of playing with the numbers. If you get stuck on a word problem, start playing around with them and then see if you can make that jump from working with the numbers to putting some letters into it. Okay? So we would have that my area, in terms of x as an input variable, would be x times 4,000 minus 2x. That looks nice. And I've got a quadratic equation. How do I know it's quadratic? Well, you don't see a square, but you know that if you distribute that through, you would have 4,000x minus 2x squared. Huh? All right, we've got a quadratic equation. Now, we're looking for the largest area. So where will that largest area occur? Well, it will occur at the vertex. So essentially, we need to find the vertex. Okay? Hey, notice that this is essentially, except for order, this is in standard form or the general form of a quadratic equation. So my best bet is to use my buddy negative b over 2a. Helps me find that vertex quickly. Now keep in mind that the b is always the coefficient on the x term and the a is always the coefficient on the squared. If you'd like to turn that around to see it better, that's what I'd have. So my vertex is sitting at, let's see here, negative 4,000 divided by negative 4. That would be 1,000. Now that's the x-coordinate. And what we're asked is, what is the largest area he can actually enclose? So we have to find the y value of this. We have to put the 1,000 in. So that would end up being 1,000 times, this would be what, 4,000 minus 2,000? We get lots of zeros on this. And I think that's 2 with 6 zeros. We would have 2 million square meters. If he has 4,000 meters of fencing, he can, maximum, enclose 2 million square meters. Now, of course, that is dependent upon not having to use any fencing for that fourth side. If he needed fencing for that fourth side, I think you realize he couldn't enclose quite as much, right? Okay, that's kind of interesting. This is one of my favorite problems. I think this is such a cool idea. We've got a parabolic archway. Have you ever seen those? You know, think about it. There are definitely a lot of bridges and so forth. There are doorways that are parabolic. By the way, the St. Louis Archway isn't quite parabolic. You can do some research on what kind of curve that is. But what we know is this thing has a span of 120 feet at the bottom, and it has a maximum height of 25 feet. I think you can tell I'm not drawn to scale, but that's okay. And I said, let's choose a suitable location to graph this archway on our Cartesian coordinate system. And I set this graph up so that you could actually consider a couple of possibilities. Now, do you think you want to just randomly stick the parabola on there? Yeah, probably not, right? You probably want to sit it in some really advantageous spot. Well, here's a thought. Set it like that. That's good. There's an even nicer one, and maybe you're thinking about that, where I would like to actually put this arch is there. Okay? I think it works out really nicely to have that 60 each way. You realize that since he's 120 feet wide from the center, it's 60 over each way, and then we're up 25 feet. And even though my arch isn't fitting perfectly there, the 120 is the inside measurement, and the 25 is also an inside measurement. Okay. Now, I've got them located, and I said, find the equation. Well, you know, we've got two equations to work with. We've got ax squared plus bx plus c. And we've got this guy. Now, does one of them look a little bit more friendly at this moment than the other? To me, this guy looks great because I know the h and the k right now. That's my vertex. So I can essentially say, all right, don't know the a yet, but this is going to be x minus, and let me put this on here just so that you're all with me. This is 0, 25. That's where my vertex is sitting. So x minus 0 squared plus 25. And I have an a value. I don't know that, but I do know he's going to be negative. And I can simplify that and say y equals ax squared plus 25. Now, I want to find out this a value in order to have the equation. So I do something that you guys have done in the past with linear equations. I essentially get another point. I say, well, 60, 0 has to be a solution to this equation, so let's put it in. 0 equals a times 60 squared plus 25. So negative 25 is equal to a times 60 squared. And a would be negative 25 divided by 3,600, which I think is negative 1 over 144. I think, if I did my arithmetic right. So now I have my equation. I have y equals negative 1 over 144 x squared plus 25. Yay! Now, what's really cool is to get to use that equation now. You know, if you weren't going to use it, why even bother finding it? Except to make your math teacher happy. Okay. Determine if a vehicle that is 20 feet wide and 22 feet tall can be moved through this archway. Now, if you had something that was 20 feet wide and you're trying to get through this archway, how would you position it? Wouldn't you position it right down the center of this thing if you're worried? Because 22 feet tall, that's pretty tall. So I'm kind of worried as to whether it's going to fit. So I've got it at about 22 feet tall, and it's 20 feet wide. So I'd want to center that thing right down through there. And so my question is, I wonder if that'll fit. How could I check that out? Well, what I could do, you realize that since it's 20 feet wide, it would go 10 to the right and 10 to the left from the middle. And so what I'd like to know is, well, what's the height of this arch when I'm 10 feet away from the center? Well, that's what this equation's for. Put in the 10 right here. So I would have y equals negative 1 over 144 times 100 plus 25. And, wow, I've got an ugly number to deal with here. I've got 25 minus whatever the heck 100 over 144 is. But you know what? I know he's less than 1. So I know that 10 feet away from the middle there, from my line of symmetry, 10 feet away from my line of symmetry, I'm going to be over 24 feet in height. Yeah, run that vehicle through. We won't have an accident. We won't knock off the roof. Okay? We're good to go. Wasn't that fun? That's a great way to use the graphing information from quadratics. So I don't think I set up a recap for some reason. Here's basically what you need to be focusing on as you work with your quadratics. You've got two forms of these equations, and they both have their advantages and their disadvantages. When you're sitting in this particular format, it's wonderful. You can just pull your vertex right out of there, okay? When you're in this format, you can pull your y-intercept out right away, but he's not as important as the vertex. To get the vertex here, we use our buddy, negative b over 2a. And where have we seen that before? In the quadratic formula. It's the first part. Okay, practice with your quadratic equations, have fun with those problems, and I'll see you next time.